So I just will not remember this. I completely forgot all first period again. All right, so we're going to go ahead and move on. You guys have about a minute to put what you think radioactive decay means. Right. 5, 4, 3, 2, and 1.
Of radioactive decay, but they all have similar patterns and similar characteristics. Our next word is isotope. An isotope is two or more atoms that have the same number of protons, but a different number of neutrons. Because they have the same number of protons, they are the same type of element, but because of the different number of neutrons, they have a different atomic mass. For example, we might have carbon 12, carbon 13, and carbon 14. Each of these isotopes of carbon has the same number of protons, which is 6, but a different number of neutrons, which is 6, 7, and 8, respectively. Next is a parent atom. A parent atom is the atom before it undergoes radioactive decay, which is followed by daughter atom. A daughter atom is the atom after it has already undergone radioactive decay. Our final important term is a half-life, which is the amount of time it takes for half of the parent atoms to decay into daughter atoms. Now, every radioactive isotope has a specific half-life. For example, carbon-14 has a half-life of about 5,730 years, while uranium-235 has a half-life of about 7.
Right, so what is a half-life? In grad school, we worked with P32, and I think its half-life was around 28 days. That might be wrong because that's been 25 years since I've thought about this. But we would take our radioactive X-ray material when we were done with an experiment, put it in a drawer and shut it, and pull it back out in a month, because then it would not be radioactive anymore. So knowing that half-life helps us use some of these things in science all the time. So what is half-life? Good, Jenna. All right, one more minute. All right, 30 seconds. 5, 4, 3, 2, 1, go.
About 704 million years. From these examples, we can see that the length of time of a half-life between elements can vary greatly, and it is dependent upon the specific isotope. Let's look a little more at this term half-life. We can understand it better if we look at a graph. On the vertical axis, we have the percentage of parent atoms remaining in that rock sample from 100% down to 0%. On the horizontal axis, we have the number of half-lives. If we look again at the definition of half-life, which is the amount of time it takes for half of the parents to decay into daughters, we can see that each half-life reduces the percentage of parents in that rock sample. If we look at this closely, we can see that at 0 half-lives, or at the moment of formation of that rock, we would have 100% of the parent atoms. At 1 half-life, half of those parent atoms would have decayed into daughters. So our percentage of parent atoms would be 50%. After another half-life, or on the second half-life, that 50% of parent atoms would have decreased by half. So it would now be 25% of the original parent atoms. And all
right, we're going to be taking our data today, and then on your own tomorrow, you'll be graphing something like this. So you're going to do your half-life and your proportion of parent atoms remaining and graph it out. You're also going to be doing putting in an actual time in seconds that will be different for everyone. Good. Okay. 5, 4, 3, 2. Yes, those are spoilers, Kate. Do not look at the chat box when you're doing your own. All right, we're moving on. That should only take a second to click.
All the rest have turned into daughter atoms. If we continue this pattern of half of the parent atoms decaying into daughter atoms every half-life, we can see that, like we said, there are 50% of the parent atoms remaining after one half-life. After 2 half-lives, there are 25% of the parent atoms remaining. After 3 half-lives, there are 12.5% of the remaining parent atoms. After 4 half-lives, there are 6.25% of the parent atoms. So in the simplest form of radioactive decay, the percentage of parent atoms compared to the percentage of daughter atoms helps us to determine the number of half-lives that have elapsed. Keep in mind that radioactive decay is a spontaneous event. We cannot look at a single radioactive element and predict exactly when it will decay. But when we look at a large number of elements, it becomes a predictable pattern. Let's compare this to what's cited as probably the most common everyday random or spontaneous event. This is a coin flip. It's true that with any single coin flip, it's impossible to predict whether it'll be heads or tails. However, if we look at hundreds of thousands or even millions of coin flips, it becomes a very predictable pattern. The results will be very close to 50% heads and 50% tails. This is very similar to what happens in radioactive decay. Just like the coin flip, we cannot predict exactly when any singular atom will decay, but as we look at a large number of them, it becomes a predictable pattern, this pattern of half-lives.
Right. How is a coin flip or Skittles or M&Ms, whichever thing you are going to use today, similar to an atom's radioactive decay? So why do we use these things to simulate radioactive decay? So put your best guess. Why do we have you? We're going to have you today using coins, Skittles, or M&Ms, shaking them up, and then looking at how many of them turn over and have one side or the other up. And then we're going to say that that number has just changed into a more stable state and emitted some sort of particle of energy and matter. Yes, you could. Well, beans won't work. Beans are good for representing the daughters that become stable, but you'll need something that's unstable that has 2 sides to be your parent atoms. But what we're going to do is I'm going to have you guys go into pretty big groups. That way, at least hopefully some of you will be able to be doing the activity and sharing data with your group if you ate your Skittles or your M&Ms, like Selena. All right, 30 seconds, or you're penny. No, hopefully no eating of pennies. All right, let's do it.
Where half of the parents decay into daughters every half-life. And as was stated earlier, each radioactive isotope has its own unique half-life, or the amount of time it takes for half of the parents to decay into daughters. Let's look more closely at how this relates to rocks. When we're talking about radioactive decay, in nearly all situations, we're talking about igneous rock. This is because when an igneous rock cools or forms from magma or lava, the radioactive clock starts from 0. What is meant by this is, in the simplest form, there are 100% parent atoms and 0% daughter atoms. This makes it a reliable clock for us to monitor the ratio between the parent atoms and the daughter atoms and use this to determine the age of the rock. And once that igneous rock solidifies, the parent atoms begin to spontaneously decay into daughter atoms. So we use these properties of igneous rocks to analyze the percentage of parent atoms compared to daughter atoms. Again, in its simplest form, we look at that percentage or that ratio to parents to daughters to determine how many half-lives have elapsed. And then we can use how long a half-life of that specific isotope is to determine the age of that rock. Let's say, for example, we have a rock sample that contains a ratio of 12.5% of the parent atom, uranium-235, and 87.5% of the daughter atom, which is lead. Using this ratio of parent atoms to daughter atoms, we can determine how many half-lives have elapsed since this rock was first formed. If we look back at our graph, we can see that a sample that contains 12.
Right. So the questions that go with your lab today will have you work backwards like this, because this is the important part of this, is how can you figure out the ages of different things using these radioactive isotopes and these half-lives. So once you plot your graph, you're going to be working backwards to figure this out. The one thing that was confusing to first period, and it's always confusing to students, is I want you to time yourself and go through 10 of these, even if you get down to zeros over and over again. Okay, so we're going to go through 10 half-lives of shaking, and you're going to time it. So at the start, and then once you told everybody in your group that you're done with your 10, you stop your time, and then divide by 10. So everybody ends up with slightly different number of seconds, and that's okay. But that's what we're going to be putting down here underneath our half-lives, exactly like the number of seconds it took for all of your Skittles or M&Ms to disappear and change into a more stable state.
0.5% of the parent atom has undergone 3 half-lives. Our next step is to multiply the number of half-lives by how long a half-life is for uranium-235. Now, if we multiply the number of half-lives, which is 3 in the case of this sample, by the length of a half-life for uranium-235, which is 704 million years, we can determine that this rock is over 2 billion years old. Now, this is a very simple example of how absolute or radiometric rock dating is used to determine the age of rocks, but it applies to the general principles and the general processes that are used to determine the age of rocks, fossils, and other items. Radioactive.
All right, and I did get an email and then went and checked on your Google form quiz that's due Sunday. There is a typo on the one question about radioactivity. The second number that says something about 10 to the negative 5th is actually supposed to be 10 to the negative 7th. So you're working it correctly, or you should notice that there isn't a right answer unless you change that second daughter atom's value to 10 to the negative 7th curies. So just note that there is one typo on your Google form quiz. All right, we are going to return now to your stream page and go physically, kinesthetically do this activity. So go to classwork, go to this week, and then you're going to click where it says, I'm on the wrong week, half-life of candium, and then open half-life of candium radioactive dating. It will allow you to make or it'll prompt you to make a copy for yourself. And what we're going to do is I'm going to be putting you into groups. And when you get into your groups, whoever has a pet that is in their house, whoever has the most number of pets goes first, and then the next person and reads the discussion, then the next person with the next number is reading background information, and then read your procedure. Okay, and then you are going to start shaking all of your atoms and filling this out. I am going to be jumping in and out of rooms to hear you reading and then to answer any questions. It takes about 5 minutes to get through usually 10 half-lives. Bread does not count as a pet or a dragon because you don't have a dragon. Okay, I guess you can maybe count your little brother. All right, are we ready to read in big groups? Make sure that if you have your pennies and your Skittles or M&Ms, whatever nearby. We're going to be in fairly large groups so that there's, before we get into groups, sorry, I need you to write, yes, you have your supplies. So put a green check mark by your name. I need to see how many of you have your Skittles, M&Ms, or pennies and something to shake them in. That way, every group has several people that have data that they're going to share while they do it. I see 1, 2, 3, 4, 5, 6, 7, 8 of you. 9, okay, good. Looks like there's quite a few of you. Good. So let's do this. I'm gonna open your breakout rooms and then I will be jumping into them to answer questions and to listen to you reading the discussion background and then the procedure. Okay. All right. Your room should be open.
Radioactive. Okay. Half-life is defined as the time required for half of any given amount of radioactive substance, parent atoms, to decay into another substance, daughter atoms. Radioactive decay is a constant process where the unstable radioactive elements break down to
Okay, I'm 14 and I turn 15 in December.
I'm 14, 15 in July.
Emily, if you were the one who had the 3 pets, you should be reading this. I just volunteered because nobody was speaking out.
Yeah, so do I?
Okay, unless you wanted to read again, then maybe we could do the second oldest.
Yeah, I don't want to read again, so whoever wants to go.
Okay. Is anyone else 15?
Did you look?
Does anyone have their 15th birthday coming up?
Actually, you could just read because I don't think anybody else wants to go.
You guys need somebody to start reading. We're wasting time to be able to do our lab.
I read the background info, but I'm also the oldest, but I don't want to read again.
Okay, thank you, Selena.
I don't care. This is also okay. So it looks like I'm done with. Okay. Oh, here's another head. Oh, another dime.
Is Caden the only one with any supplies?
Yeah.
Great question. Maybe.
I had him too.
Saisha?
I have supplies, but I don't know. Are we only supposed to one person do this, or everyone's supposed to do this?
Anybody that has supplies should be doing it.
Oh well, okay.
Oh.
What did the rest
okay.
of us without supplies do?
You are going to record the data that they're providing in the chat box. So you have some data to work with. So you can pick whatever one of the people that's sharing is most reliable or you think is
Oh,
doing it
so
correctly.
someone else is not me.
I'll do it also then.
Yeah, Gene's reliable. I trust Gene.
I am not reliable. I'm sorry.
Except for the final in 7th grade. That was clutch. You clutched. That was clutch. Yeah, that was clutch.
Wait, so we pick out all the heads?
Yeah.
The heads is the
How's this group doing?
We're doing good.
How many half-lives have you gotten through?
Oh, I did all mine. Cause I did it online because I didn't have any like Skittles or coins.
Okay.
Yeah.
Is someone in your group sharing their data in the chat box? Auto caps, I don't know. They might work. I would think that they wouldn't be equal though. I think they'd be heavier on one side versus the other. You could try. I just would think that it might be not a 50-50. But someone in your team should be sharing their data with each half-life. So people who don't have candy or pennies have data to work with.
Okay, I can do that.
Okay.
Mrs. Roberts.
Yeah.
Under the questions for this, it said it says the M&Ms represent the split peas represent the blank. But if we're using pennies, like what should we do for those questions?
You can still answer those. So the issue with the pennies in the past and with this whole activity was the misconception, right, that things were disappearing. So you were supposed to, instead of just removing the ones that are heads, or is to replace it with something else that seems stable. So you could have replaced it with dimes or something that represents that that one's no longer going through any sort of decay. So we're essentially not representing that if you're doing the penny version.
Okay, thank you.
But I just want you to know that that's not right, that what's happening, that we are actually creating something that's stable, that's still there.
Okay.
So the one side, the radioactive one, it was 149, 26, 16, 8, 3, 1, 1, 1, 0.
Yeah, that's what I got.
What did you guys get for the other side? Because, you know.
Did you guys get it yet?
I didn't get it.
I got it.
Maybe try refreshing because it says I.
Me neither. Okay, I got it.
Okay.
Right, welcome back. Want to check as everybody gets back here that everyone has data and can see my chart so that you have something to work with on the questions and the graphing part. So as you come back in, I'm checking the chat box or unmute yourself. Let me know if you did not get the data that goes in this chart from your group. Oh, it says I'm muted. Unmute myself. Why is it saying I'm muted?
You aren't muted.
I'm not muted. Okay, good. My computer is lying to me. All right. Anyone? Let me get down to the tune-in. All right. So on this is the part you guys should have filled out for your 10 different half-lives. And you'll notice that it's going right towards 0, but you never run out, just divide smaller and smaller and smaller amounts. What you're going to be doing is kind of making this plot of these proportion of your parent atoms remaining over time units and answering these questions. So figuring out what did the M&Ms or what did the pennies or what did the Skittles represent. So of the vocab that we saw in that first ed puzzle, what were those representing? And then if you had split peas or dried beans or whatever, and you use those, what was that supposed to represent? What's the idea behind what the parent atom becomes? And then number 3, how much of the radioactive element becomes stable in a half-life? And that's just using your graph and your data. What is the half-life of candium? This is according to your graph, so you're going to have to make a graph first. And then if you started with 50, would the half-life change? Meaning instead of 100 or 50 or 20, does it matter what you start with? So explain your answer on that one. And then it says, okay, work backwards. Use your graph. If you had 20 radioactive M&Ms that you found, then how many years have passed? So work backwards like the guy in the video showed you. And then it's going to have you work some problems. And then number 9 is the one of based on the actual chart for radioactive dating. Number 10 is to check that you can multiply fractions. So 1/2 times 1/2 times 1/2 times. Okay, so just make sure that you're careful. Your denominators versus your numerators, right? Stay on top versus bottom. You should end up with a very small amount remaining. All right. I will be available on demand tomorrow during your class period to answer any questions about this lab. First period requested that they have another day of being able to talk to their team about the biodiversity lab and collect photographs. So a reminder, it's a beautiful day outside. Get outside and take some pictures of all the living things that are in your study area. So you have something to share and add to your charts and graphs on part 1 of that lab, and start looking up whether the things that you're finding are native or invasive. Okay. So before we do any work on those questions right now, I want to, there's an 8-question half-life game, and I want to see how we're doing. We're going to try quizzes just to see if it's any better in terms of the Chromebooks and your Wi-Fi. So I'm going to start a live quiz. I've been using, I played one of these for anatomy over the weekend, and I liked how it gave you the 50-50 and redeem yourself options and all these other little things that Kahoot didn't do. So your code is 409304. Joinmyquiz.com is where we're headed. Let me make sure I'm sharing. Yes, I am. So I should see you get, oh, there you go.